Hi, this is Steve. I'm here to talk today about heat stress and climate change. I'd like to thank the organizers for inviting me. This is the first time I've given a pre-recorded seminar like this, so I feel a little bit tempted to say, if you're listening to this, it means I am dead. Um, I'm hopefully not, but I will be talking a little bit about mortality today. I'll also be talking a lot about adaptation. Human beings are very adaptable creatures. We live in a really wide range of climates, from uh, Arctic climates to desert ones. And so this sort of raises the question, can we just adapt to things like heat stress in a changing climate? And maybe we should be able to cope with pretty much anything. And so that's one of the things that I'm going to talk about. And to start with, a little bit about how we keep cool. So we keep cool through uh, a lot of the time through evaporative cooling. When it's very hot conditions, we perspire, and that keeps us cool. And you can even do this with something like a water bottle or Bota bag. If you get it nice and wet, then what will happen is you can actually cool it below the air temperature. And the way that works is that you evaporate the water off of the bag, and that carries a latent heat of water vapor away from the bag and makes its temperature go below the temperature of the air. Once that happens, some heat will flow from the air into the bag, and that heat flow will increase as the bag gets colder, whereas the latent heat of water vapor will decrease. And at some point, even if you keep the bag as wet as you can, at some point those two fluxes will balance, and it will be impossible to get the bag any colder. So, amazingly, if you're in a dry enough environment, you can get the water. You might be able to get the water some number of degrees colder than the air, but at some point that stops. And the point at which it stops is what we call the wet bulb temperature. So the wet bulb temperature is a standard meteorological quantity that you measure not with a Bota bag, but by taking a standard thermometer and coating it with a cloth, which you have to keep wet. And you also want to aspirate the cloth, blow lots of air over it to bring it to equilibrium quickly. And it will give you a temperature which is that temperature where those fluxes balance. And this is the coldest that you could bring an object to by wetting it and ventilating it. And any object that is at a temperature below the wet bulb temperature, even if it's wet, will warm up. Heat flux will go into it. And that is basically a consequence of the second law of thermodynamics. The wet bulb temperature is a measure of the entropy of the air. And a paper that I put up on the website that I did about 10 years ago now with Matt Huber, in this paper we pointed out that what this means for human beings, since they have a core body temperature of around 37, is that if wet bulb temperatures get above 35, it becomes impossible to sustainably dissipate the metabolic heat that your body is always generating. So you're definitely going to be in some kind of trouble by that point. And so we pointed out that this was a limit to how much heat and humidity people could withstand, in spite of our ability to adapt to lots of different things. And one of the things we showed in the paper is that if you look at the distribution of this quantity in the maximum values of this quantity around the world today, it has this histogram shown here in red, which has a kind of amazingly catastrophic cutoff at around 30 degrees. You hardly ever see wet bulb temperatures higher than 30, which is interestingly close to this sort of 35 to 37 degree point at which you get into problems with the human body. The 35 degree, 37 degree difference is because you need a couple of degrees to get heat from the core of your body out to the skin. So, so this catastrophic cutoff is, we argued, due to a feedback involving convection. It turns out that the wet bulb temperature, for the same reason that it plays this role that I've just told you about, is also directly related to the temperature that an air mass will have if it rises in the atmosphere adiabatically. And so it controls the convective instability in the atmosphere. And if it goes too high, you'll get a thunderstorm, and lower wet bulb temperature will be brought back to the surface. And so we argued that this gives you this kind of cutoff where you see lots of places in the Earth where wet bulbs come close to 30, but never where they go over it. And we also showed that this curve slides to the right by about 3/4 of a degree for every degree of global mean warming. So at some point, you would start to get wet bulbs that are close to 35. Now, some studies since then have looked at some elements of this. So for example, a PhD student, Zhang and Fuglestaller at Princeton, have looked at what happens if you take your temperature and water vapor data and you sample it only where it's raining, because that's where this mechanism should work. If there's no rain, there's no convection, and then you don't necessarily have the thermostat operating. And what they find is a very flat distribution from 20 south to 20 north, shown in the upper right here, of boundary layer. It's effectively the same as theta E or wet bulb. It's the moist static energy, but you can think of it as, for this purpose, as being equivalent. Very flat distribution, the same on land and ocean, and pretty much uniformly lifting in warmer or cooler, warmer climate scenarios. Whereas if you just look at the variable itself, which is the middle plot here, it's less uniform. So that kind of supports our idea, and it explains why you have faster warming, for example, on the continents than on the oceans, which, as you see over there on the left, which is showing the 20-year return maximum temperature, how much that will go up around the end of this century relative to the end of the previous century. And you can see, of course, that it's quite uneven. The continents are warming a lot more than the oceans. Some parts of the continents, like Europe, are warming more than others. But it turns out Europe is also getting a bit drier in the simulations. And areas that you see warming less, such as the Sahel, are in the simulations becoming rainier and having higher humidity. And so when you look at quantities like the moist static energy, it's much more uniform. And that makes changes in wet bulb more predictable than changes in temperature, which is kind of interesting. You might not have expected that. Okay, so all of this work suggests that there's kind of a limit to wet bulb, and it might be slowly creeping up with global warming. But there's an interesting study that came out this year which looked at the multi-year maxima of wet bulb temperature at stations, and they found a few stations around the Middle East where they're already reporting wet bulbs of 33 or even 34. And I was a bit skeptical when I first saw this, but they did a lot of work to try to kick the tires on this. And it turns out that the Persian Gulf already reaches temperatures of 35, the water itself, on some occasions. And that can give rise to very hot and humid air, which occasionally goes on shore, only for very short periods of time. And so there appear to be a few places on Earth where we're even closer to this limit than we thought. And so those places may be the canaries in the coal mine as the world continues to warm and we start to see higher wet bulbs everywhere. So I've been talking a lot about wet bulb temperature, but that's not the variable that people usually use to measure heat stress. The most common things that you see around are things like heat index or apparent temperature, or something called the wet bulb globe temperature, which is shown in the. I've compared these in the three panels here on the upper right. So the color is showing the quantity and on a scale that's appropriate for that quantity, where for a sort of typical temperature and humidity, they've all got the same green color. And then in the upper panels, you got temperature on the x-axis and relative humidity on the y-axis. And basically what you get out of this is that these quantities differ based on how sensitive they are to humidity. So the wet bulb temperature is the most sensitive quantity to humidity that there is, because it's, after all, defined for an object that's completely wetted. So if you ask, when are these relevant? Wet bulb temperature is relevant if you've just jumped out of the swimming pool, or you're completely doused with water and you've got a wind blowing on you. And that's seldom the case, which is why wet bulb temperature is not traditionally used. These other ones on the right are better indicators of how you're going to feel, because they effectively assume that only a fraction of your body is wet. And usually that's the case. You'll be perspiring on part of your body, but a lot of your skin will be dry or only slightly moist. You'll still losing vapor through your pores and so on. But the apparent temperature is probably the one that would be relevant for typical activities. WBGT is used a lot for sports and by the military. There's a table there on the left showing different ranges. There's a kind of color scale that dictates what activities they'll allow. The Australian Open is shut down when the wet bulb globe temperature goes above 28, et cetera, et cetera. These indices all depend mainly on temperature and humidity, except that the true wet bulb globe temperature, which is measured by this funny looking device on the lower left here, is meant to kind of emulate a person, and it also accounts for radiative heating and wind. But if we're interested in climate change, we expect a future climate to have a higher temperature and higher humidity. We don't necessarily expect winds or sunshine to be systematically any different, and that's been looked at. And so for thinking about climate change, typically studies will not try to incorporate wind or sun, and we'll just look at a simplified WBGT that only looks at temperature and humidity. If you're interested in heat stress, you also have to think a lot about not only what quantity you use, but also the duration of events. So heat waves are defined based on how long they last, and data show that the longer they last, the more people are affected, even if the temperature isn't any higher. And also, nighttime temperatures are quite important for health. And both of these speak to the fact that the human body really needs time to recover. It can take a fair bit of heat, but it needs time to recover from that. Okay, so because these heat and temperature combined measures that determine heat stress are relatively uniform, for the reasons that I've pointed out, it means that unprecedented values emerge pretty quickly when you start warming the globe. And so here's a recent study which looked at the emergence of WBGT values in excess of several thresholds. These are very high thresholds. And the scale here is logarithmic. So the light yellow regions are places where you hit this threshold maybe once every few decades. And the darkest areas are places where you hit this threshold for weeks at a time every year. And the main point here is that you can go through, with just a few degrees of global warming, massive increases in the exceedance of these thresholds. They emerge quickly in the tropics because there's not so much natural variability there. So that's where you really start to see things pretty soon that are new. Something I'm not going to talk about also is urban heat island effects. So most of the maps that you see, model projections, etc., are just the background heat and humidity. And if you live in a city, you have to add on top of that the extra heat from the city, which may also increase in a warmer climate or in a more populated city. Now, we're interested in this because of the impacts it has on ecosystems, people, wildlife, farming, etc. And it's really hard to quantify those things. There's a few reasons for that. One is that the reporting of heat-related mortality and injury is not systematic, and it can be difficult to detect. And so, for example, in Africa, heat stress tends to happen at the same time as droughts, and so it's hard to tell, and people usually attribute it to the drought and not to the heat. In Australia, we had a very severe wildfire season about 10 years ago, killed well over 100 people, but twice as many people died from heat stress as from the fire, and we only know that because of very careful work to tease it out. That sort of work in the tropics, where we have the worst heat, is often not done. Another problem is that to attribute something to heat, you really need to model the system, and we don't have good quantitative models of complex systems like people. There are models around of heat stress on humans. I think in a previous slide, I forgot to mention the Universal Thermal Comfort Index. Is a very complicated measure that has been developed in Europe based on a very complicated model of a human. But even that is only modeling how you feel. It's not going to model what the impacts are on your organs or other things which end up determining the health outcomes. So you'd like to go to empirical data, but then you have the problem that we're having unprecedented things happening. It's hard to extrapolate from current data what's going to happen when things occur that are unprecedented. And empirical studies are affected by problems of causality and how you interpret them and confounding factors. So for example, if on a warm day somebody goes out and plays football and gets injured, but on a really hot day they stay home and put the air conditioning on, you could get a misleading interpretation or impression of how dangerous different heat levels are just from a statistical analysis of data. Nonetheless, we occasionally see major heat stress events that kill thousands or tens of thousands of people. We had the European heat wave of 2003. There was a Russian heat wave in 2010, and so on and so on. These are reportedly killing tens of thousands of people. So we know that this happens, and it's just hard to pin it down. And how it will change in a warmer climate is even harder. So here's a kind of classic study from Gasparini et al. In the Lancet, where they looked at a whole bunch of cities around the world and went ahead and did the regression calculation, which I just told you has issues with it, to see what is the average death rate as a function of temperature, taking out seasonal and weekly variations. And they always get a kind of consistent sort of U-shaped picture where there's an optimum temperature where the death rate is the lowest, and then it goes up above and below that. But a couple of really curious things come out of this. One is that the optimum tends to go up and down with the background climate. So in Sweden or London, their optimum is at 19 degrees, and they start having increases in deaths above that, whereas in Thailand, the optimum is 30 degrees. And you find that pattern pretty much everywhere. And so this is telling you that there's a huge role for adaptation. People are dying not when the temperature is high or low in any absolute sense, but when it becomes unusually high or low where they live. And so it then becomes very difficult. What does that mean? You can't just take these curves and assume they'll stay the same in a warmer climate, I would say, although most of the estimates of how future mortality will be affected do just that because they don't know what else to do. But clearly, what you're measuring is not a physiological effect, but rather a kind of a societal response that includes many different kinds of adaptations, including behavioral changes, cultural, the infrastructure, and so forth. And another thing is that most studies have tended to look only at temperature, but as I pointed out, humidity is really important, and there are a few studies out there that have detected independent roles of higher humidity in driving heat stress related health impacts. So if you're seeing all this adaptation, it kind of suggests that a more robust, measurable impact of heat stress is going to be in people's behavior and in their ability to do work and be productive, rather than just whether they die or have health problems. And so this is another new study by Orlov et al. Where they've quantified productivity loss as a function of WBGT, and you can see it's pretty severe, going from typical values you'd see today, very low productivity losses, but if you increase it above 35 or so, you start to get work productivity falling below 50%. And they've calculated the economic impacts of this, things like a couple percent of GDP by the end of the century. And some interesting aspects of their work is that they've used models that incorporate a lot of different factors, including air conditioning adoption. And so just for your interest, here's a plot showing where they project air conditioning will be taken up in different parts of the world. And there's lots of places, in fact most places, that don't have air conditioning now are projected to have nearly universal air conditioning by the end of this century. So there's a lot of impacts of heat that occur through people's adaptations rather than, including also changing the patterns in the way they work, such as taking afternoon siestas. Okay, so another interesting study that came out this year, Zhu et al. Looked at historical patterns over time of where people have lived and determined a mean annual temperature range that seems to be where people tend to like to live the best and like to live and where they thrive. And so here's just a map of where they find the best places to live to be today and where they will be in 2070, and the difference is down there at the bottom. So you can see pretty much throughout the tropics it's going to get harder to live, including unfortunately here in Sydney where I am, but you Huskies are luckier. You've still got some room to go, and looks like you'll become more habitable at least by 2070. Okay, so all of this, all these questions around adaptation kind of take us back to where I started the talk, which is around limits. And we found that, okay, it's very hard to tell what's going to happen because the statistics that we have today are dominated by, because people do adapt, and that's what we see right now. Could we get to this deadly threshold of 35-degree wet bulbs in much of the Earth? And it turns out, yeah, if you look at RCP 8.5 past this century to the next century, then in that scenario, you will definitely reach the point where lots of the Earth is beyond this point. I hope that's not a very likely scenario at this point. We've already got enough transition to renewables happening that it leads one to think that RCP 8.5 probably won't happen, but at least we hope that. And the others scenarios, as you see here, don't reach this limit. So other than maybe around the Persian Gulf, we don't expect much of the Earth to hit it, but we get a lot closer than we are now, which is still very concerning. Earth's past has seen much warmer temperatures than what we have today, also colder ones. It's probably a little hard to see this, but the data around the Eocene, which come from ocean sediment cores, oxygen isotopes in there, suggests temperatures of maybe 10 to 15 degrees higher in the Eocene than what we have today. So that's well above what we're talking about. And there's some interesting hints in the geologic record, including the dwarfism of things like the horses during these warm climates, to suggest that there were impacts of these warm temperatures on life at the time. And so who knows, maybe in the future you'll see human dwarfism as we try to cope with this climate change any way we can. So in conclusion, I guess there's a few points that I would make. One is that humidity is really important to heat stress, and it's a variable that isn't included in a lot of heat stress studies, but it should be. It tends to mask naturally occurring heat stress variations, but amplify the global warming ones, because the parts of the Earth that are dry tend to be hot, but in a globally warmer climate, both the temperature and the humidity will go up. They won't go in opposite directions. So I think this is something that's not on our radar as much as it should be because of that masking effect, and it will be really important. And it means that only a few degrees of warming can bring us to significant increases in heat stress. They're hard to predict. I think there's a great opportunity here for work between behavioral scientists, public health scientists, and physical scientists to try to develop more quantitative models that can explain patterns like the ones that we saw in the Gasparini et al. Paper. And if you can explain those, then I think you can really have a better feeling that you can predict the future. Adaptation is something that is crucial to interpreting all the data that we have and to what happens in the future. But there are limits to adaptation. And if we don't do a really good job of mitigating climate change, we're going to get a lot closer to these limits than we are now. And I think that's going to make heat stress a severe issue. And you're going to see big increases in climate-driven mitigation. And I'll stop there.